think it has started. Yeah, the lecture has started. Okay, so so as I introduce myself also and regarding the topics, what it is there in your syllabus. So we'll start about the study of the laser thing. So I don't know why my slides is not changing. Okay, okay, okay. So what is laser? The full form of the laser is basically the light okay, my point. Yeah. So the laser full form is basically the light amplification by stimulated emission of the radiation. This is the full form of the laser. L means light, A representing the amplification, S stimulated emission, and R representing the radiation. So you can see that this is the green laser, which is made up of neodymium YAG laser that we call. And you can see that this laser is very intense, and also it has a parallel beams of the light, not diverging, right? And it is passing through the lens. Some lens are there, and it is 100% transmitting also. Okay, so it is like a light, which is how we can produce them this kind of the um, straight parallel beam of the light as compared to the other system when we talk about. So basically the laser are the devices that concentrate the beams of the light. Beams like any of the light is consist of what? Electromagnetic spectrums. Like, so suppose you have a sun light source, okay? You will have the different wavelength of the light and different phase, different crest, trough, okay? So it will have different frequency ranges also, and so that's why you are able to see the seven color when it pass through the prism, right? So if the sun, which we are getting the light from the sun, it will have the different many frequencies, different color, and the non-coherency. Non-coherency is basically when you will have the different phase. Since you can see you have red, yellow, and blue, so they all have different frequencies of the light, as well as their phase are also different. Okay, so now if you're talking about the bulb, okay, so in bulb basically made up of some element like we call as a tungsten. Most of the bulb used to made up of some element that they used filament we call the tungsten. So tungsten will have some its own uh, frequency and the wavelength of the light. So how it basically produce? We apply external internally we apply the voltage power supply, so that the filament which is present in the bulb that get excite, and because of that you get the bulb. But this has a wider area. You can see it can emit the light from everywhere, right? So it will be like we can say you will get one frequency range of the light, but you will get one frequency of the light, but and also it will be a non-coherent. But as non-coherent means you will have the different phases of the light. So in bulb also, since it is very diverging, so your phase will not be as same as compared to the laser. So the laser property is like it has very small hole, you can say, from where the light can able to pass it. Okay, so in the laser you will get a one frequency, one color, and coherent system of the light. Coherent means you can see all three wavelength of the light. Wave nature of the light is having the same phase, same wavelength, same amplitude. Okay, so if it is present in any of the electromagnetic spectrum of the light, then we can say that it is a coherent system. Okay, so if we are comparing in the sun, bulb, and laser, sun and bulb, the sun will have many frequencies, but non-coherent. Bulb will have one frequency, but it is still a non-coherent system. But in laser, you will have the one frequency of the light, one color, and the coherent. Okay, so this is the property of the laser. So light, what we say is the form of electromagnetic spectrum, and it behave as both particle as well as wave nature of the light. So particle nature in photoelectric effect given by the Einstein that we have studied, but in case of the light, it shows the wave nature of the light. That's why we are able to see our light sources in the form of the wave nature. Okay, so what the light that passes through the gain medium all end up with the same color. So that we will study what is the gain medium. So exactly the laser basically will have the same wavelength, same direction and the polarization. Okay, so next, uh, okay, so I just a second.
The audio is switched off.
Okay, okay. I'm sorry. At what time it got switched off? Just now, right?
When the slide got changed.
Slide is changing or not?
Yes, it changed. From then we couldn't hear.
Okay, okay, okay. So what I'm saying that the laser, as we studied, the light amplification by stimulated emission of radiation. So the radiation, the wave of the light basically emitting by a laser beam. So from where this radiation is coming? Okay, so the radiation basically is coming from uh, some crystal or the molecule. So here now the chemistry started. Okay, so chemistry is that in the laser light source, you will have some molecular crystal such as neodymium, Yak crystal, CO2 also we use. Carbon dioxide molecule laser also we can also produce the laser light. Okay, so here some example you can consider like some ruby crystal. Okay, it will have lots of millions of the atom that is defined by the Avogadro number 6 into 6.022 into 10 to the power 23, right? So that much number of the atom will be there. We are considering only one atom, suppose. Okay, so one atom is basically you will have nucleus surrounded by the electron. Okay, so here it is written a stable atom with surrounding electron. Now what you are doing is like you are applying some energy, that is the photon energy. Okay, so this photon energy, what it will do is like you will have electron. So once you will have the electron, this photon energy will undergo excitation. So this electron will knock out from the orbitals surrounded by the nucleus. So these you can see this is the electron which is knocking out of the atom. So it is going away. So once it is going away, that we call as excited state. Okay, so it was initially in the ground state. Once the photon is emitted on the atom, it is undergoing into the excited state. And once, since it is an excited state, so every system want to be in a stable state, right? So every system want to be in a stable state. So what will happen? These excited state again will come. This electron, excited state electron again will come into the ground state. Okay. And by doing so, what it will happen? It will release the release the energy in the form of the photon. So once it will go from excited to the ground state, it will release the photon. So here you can see that suppose you have you have seen that one single atom, how it basically behave and how the photon energy emitted. So but in ruby crystals, you will have the lattice. Okay, you will have layers of the lattices. So each lattices will have its own photon energy will emit. Once the photon is incidenting by input source, then once the stimulated emission means the from excited to the ground state, once the electron is coming, it will emit the lights. Like, so every atom, once it will emitting the light, what will happen? We are now amplifying the light. Okay, so it's like a combination of the all the lights are forming, and that's why you are able to get the very high intense light source. And it is very rapid process. It doesn't take uh, more than a nanosecond. Okay, so it is like a picosecond or femtosecond lifetime. So that much fast this light get amplified by different atoms. Okay, so you can say that the light is amplifying, or you can say that a photon is fired at a group of the atom, and a chain reaction of the light basically bursting out. That's why you are able to get a very high intense source of the light. We will study each step later how it basically occur. So these one emission of the light from the single atom, that we call as a stimulated emission. Okay, so there are different processes occur. So as I said that the light is amplifying, so it can propagate over long distance, and also it doesn't absorb by waters. Okay, it doesn't, and as we have seen that it was not absorbing by the when it is passing through the lens also, it was 100% transmittance. So what are the properties of the laser light that we have to study? Is the coherency that we have seen. Coherency means you will have the different same wavelength of the light with the same phase. And high intense, why? Because the light is getting amplified by different lattice of the atom. Then high directionality. uh, Directionality means collimation. Okay, collimation means parallel beam of the light, which we will study. And high monochromaticity. Monochromaticity means a single wavelength of the light. Okay, because it is coming from a single uh, crystal, such as ruby crystal or the neodymium crystal. So only one wavelength of the light basically it will emit from the laser source. Okay, so that's why we call as a monochromaticity. So next, uh, yeah. I think this one only, right? Yeah. So what is the principle of the laser? Okay. So here you can see that the in the outside figure, but inside how basically this laser light is getting amplified by the stimulated emission. So you can see that this you will have the reflective mirror. The electron, which is this green part, you can say that it has a some molecular crystal. Okay, some made up of some crystals that will have its electrons and the atom. Okay, and here you can see that photon is emitting because we are applying the internal sources. Okay, and then it is undergoing reflecting mirror, and also you will have some focal convex lens that will focus your beam of the light in one focal point, and then you will be able to get the laser beam that we are going to study later. Okay, so inside part of the laser basically work like this. Okay, and here also I think you can see that so this is like a optical pumping basically occur, and you will able to get a various emission of the photon light in a single wavelength. Okay, so it is very fast process. So what's the process basically involved is the absorption, spontaneous emission, stimulated emission, population inversion, optical pumping. Okay, and one more thing that is important, basically where you will be able to get the photon emission only when your thermal energy will be higher than your uh, incident photon. Okay, if it will be higher, then only from the ground state the electrons will undergo excited state, but that we call as a stimulated emission. Okay, but that we see in our laser. So in the laser basically the important principle that work is the stimulated emission, but in spontaneous emission you will not have any kind of the laser, because the light that is emitting, you will have incoherency. You will not have a coherent wavelength of the light. So you will get the light, but it will not be a coherent. Okay. So stimulated emission, if it is occurring, that means it is a property of the laser. And if it is a spontaneous process, that means it is just a normal lights, visible reason lights you are getting. Okay. So now here, yeah, so we will study line by line each slides. Okay. Yeah. Okay, so what's the first procedure that occur is basically the absorption. Okay, so in the absorption process, as I told, you have taken any of the molecular crystal. Okay, so you have one atom, and in one atom you will have the electron. So this is the electron, and if the electron is in its ground state. Okay, it will have energy. So have you studied about the hydrogen in quantum mechanics? The energy level of the hydrogen atom. Okay, I think you have studied. I think in the 12th also, 12th class also, it was there in the chemistry courses. Okay, so these are lines are basically representing the energy levels. Okay, so this electron, you can say that it is in a n is equal to 1 number of the cell, n is equal to 2 number of the cell, or n is equal to 3 number of the cell. We don't know, but it has this E1 is representing the ground state energy, where the electron is very stable. So what you are doing is that externally you are applying the photon to it. Then what will happen? These electron, due to giving the energy from externally, undergo excitation from ground to the excited state. And this excited state is represented by the E2. Okay. And the energy difference between E1 and E2 is given by E is equal to h nu E2 minus E1. Okay. And one more thing, that this rate of this absorption depend upon how much the number of the atom present in the E1, and also how much, what is your power density of your incident photon. Otherwise, the electron will not excite. If your power density will be lower than the electron energy which is present in the ground state, then the excitation will not occur in the E2 state. So this is the criteria, or dependency, or the factor you can say, where these electron depend upon the excitation, depend upon the rate of the absorption, and also the number of the atom that is present in the E1, as well as the spectral power density of the radiation. Okay, now the thing is, second step. The second step when we are coming is the two label laser. Okay, so first in normal laser, basically two label laser are not good, but this is the initial process to produce the single beam of the laser. Okay, so spontaneous emission, what happen is that, as I said, this electron is excited from ground to the excited state. Now it has reached to the excited state. Okay, so what will happen is that every system want to be in a ground state. So this electron is already in the excited state. So it want to be again going back to the uh, ground state, because we applied some driving force externally. That's why it went to the higher oxidation state. But now it is going to the, now this electron want to go into the ground state. Okay, so in going to the ground state, what will happen is uh, it will emit the emission of the radiation. In doing so, when once it is coming from E2 to E1 state, what will happen? It will release the uh, light in the form of the photon. Okay, so emission, when it happen, it will be random. That I say, just now I said, is the incoherent. Okay, and it will not have the same phases as compared to the coherency. So it become incoherent. So a spontaneous process always become incoherent. Okay, but when we talk about stimulated emission, what happened in the stimulated emission? Same procedure. We applied photon in the ground state, and the electron went to the excited state. Now, what happened is that this electron again we excite externally, so that it can undergo in the ground state. Okay, and then once it is coming to the ground state, it will release the photon. So what will happen? The externally that we applied the photon in the excited state, that photon, as well as once it is going from E2 to E1 state, that photon basically combine and produce a double photon beam, and it will have the coherency, means having the same phase and the wavelength of the light. So basically this coherency produced because this emitted photon undergo one non-radiative transition, which we will see, and that non-radiative transition undergoing the ground state. So that's why we call as a metastable state. So emitted photon basically undergoing a metastable state, and instead of producing one single wavelength of the light, it will produce the uh, two time double of the wavelength of the light, because we are exciting externally these excited state electron to undergo into the ground state. Why it happened? Because what happened is that in the excited state your electron is stable. Okay, generally if it is not stable, it immediately undergo to the even state and release the photon. But if your excited state is stable, then in order to come back into the ground state, you have to apply the external sources. So once we are applying or amplifying the excited state energy level to go into the ground state, it will emit the two time higher photons and with the coherency. Okay, so this we call as a stimulated emission. So this is what basically happen in the light. Instead of getting single wavelength of the light, we are getting the double two time high power of the light. That's why we are able to get the high power intense laser of the laser light. Okay, and also these stimulated emission depend upon how much the number of the electron present in your excited state energy state. If your number of the electrons will be lower than the ground state, then in that case the laser will not produce. Why? Because the meta step that we call as a population inversion, okay, that we will study. So it's like a in order to produce this high beam of the electron source, your excited state electron also should be higher, that we call population inversion. Okay, so and also pumping, so that we call as a optical pumping of the laser in the principle of stimulated emission. Okay, so here, okay, next. Yeah. So so I will ask you the question is like, what's the difference between spontaneous and the stimulated emission? So whatever I explained is basically in the spontaneous emission, the result of transitioning of an atom from excited state to the lower energy state. As you can see from the excited state to the lower energy state. This is the happening in the spontaneous emission. So exciting state to the lower energy state happen due to natural. We are not applying any external things. Okay, naturally it will have the tendency to attain the minimum energy to the ground state. Okay, no external agent is involved and result in the ordinary light. And whatever the light obtained is not coherent. But in the case of the stimulated emission, as we have seen, you can read back and see the slides. In the stimulated emission, you have electron present in the excited state. So what it is telling is here, the stimulated emission of radiation is the process in which the photon are used to stimulate an atom in an excited state to fall to a lower energy state. So we are externally applying uh, the energy to fall into the lower energy state, and the photon need to be incident as a acting as a stimuli, external stimuli. That's why we call as a stimulated emission, and can be used utilized to get the laser beam, and because of that we get the coherent light obtained. So this is the, you can see the table of how the transition is happening. Okay, so this is a chromium crystal. They have used the chromium containing some laser. What it is happening is that this point is indicating the ground state. So what they have done is like they absorbed some light. Some light has been observed. Because of that, the electron undergo excitation and reach to this state. So this is even state. Once you will have very high source of the electron, then these electron will excite from ground to the another high level state. Okay, so after that, what will happen is that in order to emit the laser, it undergo non-radiative transition. Okay, so this is non-radiative transition because here the emission of the light will not occur. And why it is occurring? Because they found some other state uh, near to higher energy state level, and that's why here instead of here the electron is more stable in the metastable state. Okay, so the electron is more stable in the metastable state. So these excited state electron will prefer to go into the metastable state. That's why we call as a non-radiative transition. And now from here, the electron basically pumped up. We apply external agent, and due to the external agent and depend upon how much the number of the electron excited in the and is stable in the metastable state, and that much amount of the output in the form of the light emitted with a specific coherency and the wavelength nature. And then once this external electron we are emitting the light, all the electrons will go into the ground state. Okay, so that's we call as a stimulated emission. So stimulated emission basically occurring from the metastable state to the ground state and emitting the very high intense source of the light. Here for the ruby crystal, it is shown that the red light which is emitting has been the wavelength of around 694 nanometer. Okay, so this is how the process of transitioning occur in any of the crystals you can take. So if you are talking about number of the level of the system, this comes into the category of the three level system. Why it is a three level system? Because you have ground state, excited state, one transitioning, or it can undergo one to above higher state transitioning. So E1, E0 to E1, or E1 to E0 to E1, E2 state, and then E2 to E3 state, and then E3 through E0 state. Okay, so this is called the three level transitioning that also we will study and differentiate between 3 and 4 and 2 level transition. Okay, so this is the principle how the transitioning is occurring, and it is very fast process. It occur in the femtosecond or the picosecond picosecond lifetime scale. So these transitioning, if you are saying, it will occurring on only the like a 10 to the power minus 14 second per second, like that. But in metastable, the electron basically reside for some time. So that's why we apply external agent. That's why you are able to get the laser beam. Okay, I hope you are understanding. So now here with the number of the molecule, as I told you that the for emission of the laser, what important is the population inversion. This you have to understand properly. I will give you next slide the question, and you people have to solve it also. Okay. I will solve. I will try. I will solve, but you people have to tell me that what we can do. What will be the answer? Okay. So the population inversion, as I told. So what is basically this? As we know that in the initial thing, generally what we see in the molecular, in the ground state, you will have the atom which is having different number of the electrons present in the orbitals. So suppose here you have a 5 number of the electrons in the ground state. So this is E1 and this is E2 energy. So the N1 is representing the number of the electrons present in the ground state, N2 representing the number of the electron present in the excited state. Okay. So here you can see that in number of the electron present in the ground state is higher as compared to the excited state. So this is the general criteria. Why? Because when we are applying the photon to the ground state, what will happen? Only some of the electron absorb that energy and undergo the transitioning to the E2 state, right? But if this in population inversion case, what happen is that you will have the number of the electrons present in the excited state more as compared to the ground state. If it will occurring, then you will be able to get the laser. Okay, so this process is called as a population inversion. How you can able to amplify? Why? Because now the number of the atom present in the excited state is more. So what will happen? We are applying externally the stimulus. So most of the number of the electron undergo amplification and emit the light. Okay, so but in this case you have only two electron. Okay, so in this case, you will not able to get the laser. You will have only incoherent spontaneous emission kind of feature. Okay, but here you have a higher number of the molecule. So you will get the high intense wavelength of the light. Okay, so here this formula, according this formula given by the Boltzmann. So Boltzmann equation, I think you have studied in the chemistry also, like which is in the statistical mechanics course, I think. So there also you will have the number of the labors and how much the number of the electrons it transitioning, that we can calculate, and it depend upon exponential feature. So N2 representing the number of the electron in the excited state, N1 representing in the ground state, which is equal to the, according to the Boltzmann equation, e to the power minus delta E by kT. Okay. So delta E, what is delta E? We have seen in the previous slide, the delta E is basically this one. Okay. So delta E is basically E2 minus E1. Excited state subtracted ground state. Okay. So this is delta E. Yeah. So here this is delta E. K is the Boltzmann constant. T is the temperature. Basically KT we call as a thermal energy. Okay. So when the KT is larger, suppose your thermal energy is larger. Okay. So the ratio, what it will be, suppose this value is very high. So what will happen? Delta E by infinite. Okay. It will be 0. Okay. And 1 upon E to the power 0 will be 1. So N2 by N1 ratio will be 1. So that means your N2 is equal to N1, means number of the excited state is equal to the number of the ground state, right? Now, if you see, when your KT is a small, KT is a small means you will have 0. So delta E by 0 infinite. So 1 upon E to the power infinite is equal to infinite. 1 upon infinite will be 0. So N2 by N1 is equal to 0. And all the molecule, what does it mean? It means that all your molecule is in the ground state only. Okay, no any molecule has undergo the excited state. Okay, so based on this population inversion formula, so can you solve this question? Okay, yeah, it is simple only, nothing is given. So what you have to do, you have ground state, the ground state and the excited state of laser is separated by 1.8 delta V. Okay, 1.8 delta V, that means what is separated by? Separated means delta E it is given. Delta E it is given 1.8 electron volt. Okay, so what you have to calculate is the ratio of the number of the atom in the excited state to the ground state, and the wavelength of the radiation that is emitted at 27 degree Celsius. Okay, so can anyone solve it, and just try to solve it? It's nothing, just use this formula where I have showed you. N2 by N1 is equal to E to the power minus delta E by KT. Are you people trying to solve it, or let me help you? Just you put everything in the formula and see if you are getting this answer. So the wavelength of the radiation, wavelength of the radiated light should be that much, and ratio will be the number of the atom that will be present will be this. Let me try to do it. So, okay, so what I'm saying is that you have to use N2 by N1 is equal to E to the power minus delta E by KT. Okay. So we know K value is constant, that is 3.18 into 10 to the power minus 23 joule per Kelvin. Okay. And what is temperature? Temperature is given 27 degrees Celsius. So you will convert it into the Kelvin. So what it will be 300 Kelvin, right? So now you apply everything. You have given delta E. Delta E is 1.8 electron volt. Okay. So here you have E to the power minus 1.8 electron volt means electron one electron energy 1.6 into 10 to the power minus 19. Okay, in the form of the volt. Then k put the value of the k 10 to the power minus 23 and t value 300. Just solve this thing using the calculator. It will be easy for you. Hello. Hello.
Yes, we can hear you.
Are you solving? You got the answer? Are you getting N2 by N1 value 6.14 into 10 to the power minus 31 or not?
I have a question.
Yeah.
Isn't Boltzmann constant 1.3806 into 10 to the
Oh,
minus
yeah.
19?
Yeah, it will be 1.38. Sorry. 1.38. 1.38. Are you getting? So if you will solve this, you will able to get it 6.14 into 10 to the power minus 31. So now the next question that is asking is basically the wavelength of the radiation. Okay, so in order to get the wavelength, eraser. Okay, I don't know. Okay. It's just I'm telling you normally how you can solve the wavelength. So wavelength it is asking. What it is given for us is basically the delta E. Delta E we know. What is delta E? Delta E is a h nu. H nu is equal to C by nu is equal to C by lambda. Okay, so from here we have to get it. We know delta E 1.8 into electron volt. Okay, so we will convert into joule 1.8 into electron 1.6 into 10 to the power minus 23 जो भी है. Okay. 1.6 into 10 to the power minus 19. Then here we know h we know c we also know velocity of light 10 to the power minus 8 sorry 10 to the power 8 divided by lambda. H value also we know Planck constant 6.63 into 10 to the power minus 34, right? So when you will solve this thing, you will get the wavelength of the light, I think around 6900 angstrom. 6900 angstrom. Okay, so this is how you can able to calculate the wavelength of the radiation. So physically, are you able to understand like how we can calculate the number of the atom that undergo excitation once we are incidenting our any incident photon, and what wavelength then we used, that also we can able to get it. Why? Because all these number of the excitation depend upon the rate of the absorbed light and the power density of the incident photon. Okay, so I hope you understand. Can you tell anyone yes, no, something?
Yes, ma'am. We understood.
Okay,
Yes.
okay, fine. Okay. So next, yeah. So I was talking about this 3 label, 4 label laser. So it is nothing else. It depend upon systems to system. Okay, so what kind of the laser we are using and how powerful you want it. Okay, so in the label laser, what I told you is the basically you will have the ground state, and this ground state you are pumping by applying energy. So because of that, it undergo excited state. So in the excited state, it went instead of E1, it went to the E2. Why? Because it depend upon how much wavelength of the incident photon. Sorry. How much how much power of the wavelength of the photon you are incidenting on the ground state. So it went to the E2 state, and in E2 state we call as a short lived. Why? Because here the electron are not stable. So what they found is that the lower energy is more stable. So these the electron from here will undergo into the lower state. That lower state we call as a metastable state, and from here we apply external agent, external stimuli, so that the electron will stable. The stable electron in the metastable will undergo to the ground state. As a result, it will emit the photon. So that we call as a lasing transition. Okay, I think this much time I have repeated this thing. I think you have understood like at least basic principle how the laser we are able to produce it. Okay, and now coming to the 4 label system. 4 label laser is basically, I think, CO2. In the CO2 it work. We will study. But what happened in the 4 label, you will have 4 transition. So here you had E0 to E1, E1 to sorry, E0 to E1, E2 state. So E0 to E2 state, E2 state to E1 state, and then E1 state to the E0 state. So here in 4 label, you will have the ground state. The electron is present here. It will undergo to the excited state. So here the excited state, you have a E1. Suppose this is E1, this is E0, this is E2, this is E3. Okay, so it went to the E3 state where it was short lived, then it decay to the metastable state, then undergo, then we apply the external stimuli, it undergo lasing transition to some other state which was short lived. So from short lived, then it undergo the fast decay. So here the emission will not be a laser. The laser transition is basically occurring to this when it is undergoing to the E2 to E1 transition. Okay, so this is like a 4 label laser method. Okay, so it like depend upon what kind of the molecular crystal you are taking, and also how much the at what label your transitioning is occurring. Okay, so it depend upon that, and accordingly wherever the population inversion they will find, it will basically the electron will emit the photon once it will reach to the ground state. Okay, so this is the difference between 3 label and the 4 label laser. Okay, so if you have to conclusively, if you have to see what's the difference between the 2 label laser, 3 label laser, and 4 label laser. So in the 2 label laser, what is this? You have only one transition, E1 to E2, then E2 to E1. That is spontaneous. Okay, so it will be very hard. Why? Because the population inversion will not be high. The means in a 2 label laser, population inversion generally doesn't occur. Okay, and it is a theoretically only, experimentally we don't get it. But in 3 label laser you will have E1 to E3, E2 to E1. So here the population inversion will be moderate, and that we have seen in the ruby laser. Okay, that we will study. Okay, ruby laser. Then in the 4 label laser you will have easily the population inversion. So as I told, the population inversion is important for the emission of the laser light. So in neodymium, YAG, helium neon laser, basically this, and this kind of the laser basically used most in the medical purpose. Okay, because it's a 4-label laser and it has a very easy transitioning to undergo into the population inversion and a high intense source of the laser beam come out. Okay, so this is all about the lasers that we are studying. And I think what's the time is 7:29. Okay, we can have 5 more minute, 5-10 minute. Okay, so what's the part of the solid laser? This is just a recap and the component. See, I can take some demo, like a test kind of thing also based on these slides only. Uh, I will share the lecture slides and other thing also, but still, if you are able to capable to learn everything in the classes, then it will be more good. Okay. So here, whatever I have teased you, as I told you, the part of the solid state laser is basically when you have a solid material in the laser. Okay, so as I told, the crystal is having the solid laser, but you will have different kind of the laser. Some are gas laser also, some are uh, liquid laser also. Okay, so this is a solid laser because made up of the solid crystal. So same procedure, the process what we apply in the input, a high voltage electric flash lamp flash on and off, and every time it flashes, photon energy is pumped. Photon energy is pumped means the electron undergoing from ground to the excited state into the ruby crystal. Okay, and atom within the crystal absorb this photon energy, and their electron perform quantum leap and jump to the higher energy state. And within millisecond, the electron leap back to the original energy level. So it's like a two-level transition and spontaneously emit a photon. So now these photon bounce up and down into inside the crystal at the speed of the light and exciting other electrons also, because the as I told, it's a crystal. So what will happen? This excitation not only occurring in the one atom, it is occurring in the all the atoms. Okay, present in the this much area of the solid material. Okay, within then continue to produce more and more photon. The original flash of the light has become exponentially amplified. Okay, and here the mirror is there in the at the end of the uh, input and output of the laser. Okay, you will have the mirror. What basically this mirror will do, it has some convex lens. Okay, that we will study when we are going to study about the focal length of the lens laser. Okay, that time we will study. So it basically keep all your photon energy into one focal point. Okay, and that's why you will have a then it emit the laser beam in the form of the one particular coherent beam of the light, parallel beam of the light. Okay, so a mirror of one end of the cube keep the photon continuously bouncing back and forth inside the crystal. At the other end of the tube, a partial mirror reflecting. So it is a partial. Here you will have the only reflecting mirror, but here partial reflecting. So it will be a partial transmitted also. It will some of the light will get transmit also back into tube and allow other to escape to form the concentrated laser beam. Okay, so here reflecting mirror is important to put it in order to produce the uh, pumping source of the continuous bounce back and forth rays of the light inside the crystal. Okay, so these are the components. Pump source is important, blazing medium is important, optical resonator is important, and reflecting partial reflecting mirror and highly reflecting mirror at the both end. Okay, so this is just now I think you have understood like how basically the laser works and how photon emitted. Okay, so now as I told you, what are the type of the laser? Okay, so there are different type of the laser: the solid state laser, gas laser, liquid dye laser, semiconductor laser. Also now they have explored semiconductor laser also. Okay, so here in the solid state laser, you will have ruby laser and neodymium YAG laser, neodymium glass laser also, and gases. Gases basically in the gas laser, it is made up of like mm, neon, helium neon, inert gases. And CO2 laser is very important, I can say. Why? We can use CO2 from our atmosphere. Okay, so that CO2 we are converting into the laser, how good it is. we are minimizing the CO2 level also. So it's like a very good application in the form of the laser as well as the argon. So like inert gas, it is fine, but it has its own advantage. But CO2 laser is like a beneficial for us also, because the CO2 which we are uh, creating in the pollution. So because of the CO2 only, the pollution is increasing, so that we are minimizing using the laser. Okay, then here liquid dye laser. Liquid dye means basically made up of the dye material, some organic material film. So polymethane, curamine, so that which has the property to absorb the lights. So basically it will have a some benzene kind of ring, or anthracene, naphthalene kind of the moiety present in the these kind of the dye, which has the tendency to absorb the light and produce the different colors. Okay, so that kind of the laser also has been for developed. And also in the semiconductor lasers, like a gallium arsenic laser, indium and phosphorus laser. Okay, so these kind of the lasers is already has been explored here. And then if you're talking about the common laser that we are using, which is important for us in the medicinal purpose. Okay, so it has, so we can able to see that you have different CO2 lasers and other kind of the diode, sapphire, made up of the sapphire, krypton, helium, neon, argon. So it has its own wavelength of the lights. Okay, so whatever the laser it is emitting, it has its own wavelength. Okay, so these all are the wavelengths. It is not as important, but you should know when you are using in the medical purpose, because in medicine or in medical purpose, you will have varieties of different things, like where you are using, whether it is in the teeth, with the tissue in the gynecologist, yeah, internal part of the bodies, are so it depend upon different areas, type of the diseases, which laser will be beneficial. So so in selecting for that, you need to know that what's the wavelength is required to choose. Okay, and what's the impact of choosing this kind of the wavelength, what it will do. So once it will interact with your body system, so what will happen? The thermal, mechanical, plasma, etching, photochemical reaction, photoablation. So these kind of the things, or it can also give the imaging like in a gynecologist things. If you have to see our uh, the uterus and other things, so that basically in ultrasound also, this kind of imaging technique, using the imaging technique only, we can able to see our internal part of the bodies, right? So what are the pulse duration? Pulse duration means transition rate. Okay, so these all are the transition rate where the laser can emit that much fast. Okay, how fast the laser can emit, it depend upon the number of the transition and the population involved. So these are the typical pulse duration, and how it interact and what happen once it is interacting, whether it is producing thermal energy, mechanical energy, or other thing. Okay, so these all are the basically the common laser that we use in the medical purposes. Okay, so these all are the properties. I think I will stop this class, and we will have the class. Okay, I wanted to ask you that can we have a class tomorrow also at this time only? So if possible, I think I will stop the recording. Mm. I have to take the attendance.